A circle is the set of all points in a plane that are at a fixed distance from a central point. This central point is called the center of the circle, and the distance from the center to any point on the circle is called the radius. To draw a circle on a plane, you just need to know its center and the length of the radius. The radius is usually represented by the letter r. All radii drawn from the center of a circle are equal in length. Now let's take a look at some basic concepts related to the circle. Tangent. A tangent is a line that touches the circle at exactly one point. It doesn't cut through the circle, just touches it and moves on. Secant. A secant is a line that intersects the circle at two different points. So it enters the circle, passes through it, and exits. You can think of it as a line passing through the inside of the circle. Diameter. This is a line segment that passes through the center of the circle, connecting 2 points on the circle. It's exactly twice the length of the radius. Chord. A chord is a line segment connecting any 2 points on the circle. It doesn't have to pass through the center. If it does pass through the center, then it becomes a diameter. Arc. An arc is the curved part of the circle between 2 points on the circumference. The length of an arc depends on the angle between those 2 points and the circle's radius. We mentioned earlier that a tangent touches the circle at a single point. This point is called the point of tangency. A radius drawn from the center to the point of tangency is always perpendicular to the tangent. Let's draw another tangent. As you can see, it also forms a right angle. Perfect. Now let's draw 3 circles that share the same center. In each of them, the measure of the arc corresponds to the central angle. So the arc's measurement doesn't depend on the radius. For example, the measure of arc AB is the same as arc CD and arc EF. They all match the central angle, which in this case is 80 degrees. A full circle corresponds to 360 degrees of arc. If we draw 2 diameters that are perpendicular to each other, they divide the circle into 4 equal arcs, each measuring 90 degrees. And together, they sum up to 360 degrees. An angle with its vertex at the center of the circle and its sides or arms being radii is called a central angle. The measure of a central angle is equal to the measure of its intercepted arc. If 2 central angles are equal in measure, then their corresponding arcs and chords are also equal in length. Let's form a triangle using the center and call the central angle x. Let's assign the chord AB a length c and the arc AB a value a. If we form another triangle below with the same central angle x, we'll find that the arc and chord lengths are identical to the first triangle. Now let's talk about the inscribed angle. An inscribed angle is formed by 2 chords meeting at a point on the circle. Let's call the angle between chords AD and BD angle x. In this case, the arc AB is equal to 2x degrees. So what happens if I draw another inscribed angle that also intercepts arc AB? In that case, angle ACB would also be x. So what if an inscribed angle intercepts a diameter? Then the intercepted arc is 180 degrees, and half of that is 90 degrees, which gives us a right angle. Let's draw a few more. As you can see, any inscribed angle that intercepts a diameter is a right angle. Now that we've covered external angles, let's take a look at interior angles. An interior angle is formed by 2 chords that intersect inside the circle. Its measure is equal to half the sum of the measures of the arcs intercepted by the angle on both sides. So in this example, angle x is half of arc AB plus arc CD. Let's draw a tangent and a chord meeting at a point on the circle. The angle formed between a tangent and a chord is called a tangent chord angle. If we call this angle ABC as x, then the arc AB will measure 2x degrees. Let's summarize the relationships between central, inscribed, and tangent chord angles. If this tangent chord angle is x, then the arc AB is 2x degrees. Now what if I draw an inscribed angle that also intercepts arc AB? Angle ACB would be x. And what about a central angle intercepting the same arc? That would be angle AOB, and it would be 2x. Make sense? Let's now take a look at an external angle formed by 2 secants. Two lines passing through point K intersect the circle at 4 different points. If we call the angle at point K as x, and the arcs intercepted as A and B, then angle x is equal to half the difference between the two arc measures. Now let's draw two tangents from a point C outside the circle. As we said earlier, the radius drawn to the point of tangency forms a right angle. If the angle at point C is x, then arc AMB would measure 180 plus x degrees, and arc ANB would measure 180 minus x degrees. And now a quick question for you. Remember how we found angle K in the previous example? Do you think that same formula applies here as well? That's your assignment. Let me know what you think in the comments. Let's say we have a circle and a point C located outside the circle. From this point, we draw two tangents to the circle. These two tangents are always equal in length. Looks like it in the diagram, right? The computer drew this, so of course it's accurate. But still, let's prove it. It'll be easier to remember that way. The lines drawn from the center to the points of tangency form right angles. If we also connect points O and C and call the radius r and the length of OC as a, then by the Pythagorean theorem, we get CB squared plus r squared equals a squared. Solving for CB gives us its length. If we do the same calculation for the triangle on the other side, we'll find that CA equals CB. Next, take a look at this setup. From point A outside the circle, we draw one tangent and two secant lines. There's a special relationship between them. AB squared is equal to AC times AD. And it also equals AE times AF. This is a key identity you should remember. Now for the next diagram. We have three lines intersecting the circle and all meeting at a single point. There's another important relationship here. The products of the two segments on each line are equal. Let's prove it so that it stays in mind. First, let's remove the line GD to simplify the figure. Then, connect points BF and CE. Let's call angle BFC as x. This is an external angle, and it intercepts arc BC. So angle BEC, which also sees the same arc, is also x. Now call angle FBE as y. It intercepts arc FE, so angle FCE is also y. That means the third angles in both triangles are also equal, right? So the red and green triangles share the same angles, which makes them similar triangles. In similar triangles, the ratios of corresponding sides are equal. So, for example, the ratio of side AB to AC matches the x angles in both triangles is equal to the ratio of the sides opposite the y angles in both triangles. And if we cross-multiply, we end up with the identity we were trying to prove. Now suppose we have a circle and two chords that are said to be parallel. In this case, the arcs between those parallel chords are also equal in length. If two chords are equal in length, then the arcs they define on the circle in both length and measure are equal too. For example, in this diagram, if chord AB equals chord CD, then the arcs they define are also equal. And if AB is a diameter, and CD is a chord perpendicular to it, then CD and the arcs it cuts off are divided into two equal parts. This one should be pretty easy to prove. So I'll leave that as your assignment. Alright, I hope this was helpful. If so, don't forget to like the video and subscribe to my channel. See you soon!